Underfill in Sherlock. And with that, I will turn it over to Natalie.
Thanks, Adita. Good morning, everyone. Today we're going to be talking about how to handle underfill in Sherlock, as Adita suggested. It's going to be a pretty simple, straightforward approach. If you're familiar with Sherlock, you know it's going to be intuitive. It's not going to be anything too intimidating. Our agenda for today is going to be, just give me 1 second. My screen isn't moving forward, which isn't great. Does my slides look like it's moving, Adita?
No, they're not. I'm still looking at the cover slide.
Okay, slight technical difficulty. My slides are not moving forward. Give me 1 moment. Okay, let's do this one more time. And okay, perfect. Of course, it's when I start the webinar, things are going wrong. This worked before, I'm sure. So today's agenda, as I was saying, we're going to go over a bit about underfill, which is really old news to everyone at this point. How do we keep up with these continuously evolving materials? And finally, how do we use Sherlock to simulate the influence of underfills on our PCBAs? So first, we're going to talk a bit about, in today's electronics industry, how underfilling is a bit of old news. Before underfill, which was probably decades ago, whenever you had a component in a product go through your testing, so your drop testing, thermocycling, vibration is indicated by these icons here, you would get certain failures in your solder joints, specifically for dealing with BGAs, for example. You would see failures earlier than desired. After the invention of underfills, which happened, I think, quite a few decades ago, this helped to mitigate the problem. So under thermocycling, under vibration, under shock, applying underfill, applying this type of material underneath the components, as the name suggests, helped to prevent these failures. It helped to prevent the strain that was being applied, or some of the strain loading that was being applied to solder joints, and therefore they lasted much longer. So it's a pretty much high-level overview of underfill, a bit of motivation for why we've been doing it and why we've been doing it for so long. Now the question is, or the idea is that in today's industry, the needs for our products and the changes in the deliverables that are happening is evolving. It's coming along very quickly, and we always have to be able to continue to approach these problems and increase the reliability of our electronics. So for example, right now we have drones, we have electronic cars, we have our computers, we have our wearables, we're sending satellites to Mars, we're sending robots to Mars, sorry, we're sending everything out there. So the changes in the environments that these products are going to experience is very extreme, it's very dynamic. Because there are these different changes, these different environments, these different stimuli, there's always that increase in reported failures due to things like thermocycling in testing or even in the field, and not just thermocycling, but vibration and shock as well. So where does underfill become a little bit of a problem? Well, the use of underfill greatly influences the failure behavior and the shock and vibration. As I've said before, it was intended to help mitigate these sorts of stresses. So underfill materials can cause warpage and tensile stresses that can greatly reduce the time to failure. The selection of the correct material is critical. So this becomes very important. You can't just underfill with just any random material and expect it to do what you hope it would do. And we'll see that in examples that I present today. One of the qualities, I guess, or material characteristics that becomes very important is this quality of the material to have a glass transition temperature. So all amorphous materials, underfill materials, have a glass transition temperature. So what this means is that the mechanical properties of the materials change as a function of temperature. So as we can see, focus your attention to the bottom left image there, we'll see that as we increase temperature, there is a change in the CTE and a change in the modulus. So the changes in the CTE is due to the changes in the free volume that happens within these polymers. The changes in the modulus are driven by the increase in translational/rotational movement of the polymer change. So just to sum up at a high level, you're basically changing your CTE. Your CTE is going to increase as you increase in temperature, and the modulus will decrease. So we kind of have this opposite relationship with respect to temperature. Also of note is that the increases in CTE tend to initiate before the decrease in modulus, and this is simply because lower levels of energy or temperature are required to increase free volume compared to the increases in movement along the polymer chains. So all of this TEG behavior influences the stresses that are going to be applied on the board, on your solder joints. It's a very complicated problem to have to address. So how do we effectively keep up with these changing underfill materials? And then on top of it, our changing needs, our needs to put different types of devices and products in different environments. Should we do testing? Should we take advantage of the power of simulation? So just to give kind of a high-level view, both of these require time, funds, engineering time, but which of those is more time and cost effective? We need testing. There's absolutely no way to get rid of it, but perhaps there's a way to use the power of simulation to complement testing and hopefully derive a more effective approach. So here I have a very brief case study that DfR did where we were able to collaborate with an American auto manufacturer, and we were able to do a study on where savings would occur, essentially savings would occur, if you use the power of simulation. And just to highlight the kind of high level here, what was really important is that through simulation, we were able to see where testing could be even more effective and where savings could occur, which becomes very important when you have things like KPIs, when you have things like time to market, that become very important. It becomes very critical for you to have effective testing and also be able to save money as well. So with that motivation in mind, with that motivation that simulation can really help to complement testing, can help to have a more strategic approach moving forward, how do we simulate the influence of underfill in Sherlock? Well, to give you kind of that bigger picture view of how things work in Sherlock, if you're not familiar with it, this is kind of the steps that you would typically take. If you're one of our users or some of our users listening on this webinar, then this may look familiar to you. So I've broken things down to 4 basic steps. So the 4 steps are, step 1, you start with your life cycle conditions. So what are your environmental conditions? What are your thermal cycling? Do you have a vibration profile? Do you have any other stimulus that's going to become very important here? Next, once you understand your life cycle conditions, once you understand your reliability goals, so to speak, and that being, I want my product to last, for so long, I want it to last for 5 years. That's under these environmental conditions. That's what my goal is going to be. Once you have that in mind, step 2 involves components and layout. So usually Sherlock is able, well, not usually, but Sherlock is able to process industry design files. So your ODB++ archives, your IPC 2581, Gerber files, any of that is processed in step 2, where you input these design files into Sherlock. Sherlock processes this data and is able to produce a PCBA or a model of a PCBA very easily. Once you have, or when you have your component layout perfected, which again is just a couple clicks of work, you apply your underfill material as necessary. Next, it's a couple clicks to run the analysis and acquire really good results. And you can see how your BGA, for example, is going to survive with and without underfill conditions, with or without underfill materials under specific conditions. So that's the example that I'm going to present today. So step 1, anyone that's familiar with these, with Sherlock would know that it's very simple, kind of like filling out a form to input your shock events, your harmonic vibe events, your thermal events. Very easy to get this information that's used in tests into the simulation environment within Sherlock. The next step that I mentioned before, or step 2, is using the electronic design files, so your Gerbers, your ODBs, your IPC 2581, all information from your copy layers to your component layout, to your silk master, and so forth, are populated within Sherlock, and then a beautiful picture of a PCBA is shown in 2D. One of the other steps, or minor steps, which can be pretty powerful, especially in the automotive sector, is to define your laminate glass constructions. So usually you would, for example, use generic FF4 or an Isola or any of the hundreds of laminates that we have within the tool. One of the other things you can do is specify your laminate constructions. So for example, if we're using 2116, SEMI 628, this will affect the overall CTE and the overall modulus that you have, the effective overall CTE and modulus that you have experienced on your board. So being able to appreciate these minor details, or can be significant details, will increase the accuracy when simulating the effective influence of your PCB on your components. Within doing kind of the component layouts step of developing a Sherlock project, there's always the ability to model components in very great detail. So for example, in today's example, I'll be doing a BJ that's underfilled, and we'll see a bit about that later. There are also a significant range of packages that are built into tool, and then you can take advantage of that depending on what you need. Within the tool, there are also, just an FYI for everyone, again, this is more for users that, or more for the audience that is not as aware of Sherlock. There are several libraries within the tool that allow you to take advantage of different laminate materials, different part libraries, package manager, and if you're not able to find what you're looking for, we have a librarian team. And our librarian team is able to pretty much produce these Sherlock definitions that you need to complete a successful project. So moving on to the example for today. So today's example is basically showing how to do, or how to handle, underfill in Sherlock. So I've chosen a specific BGA that I've modeled here, again highlighting in the 3D view what the BGA would look like, and that's in the top right image in that general section there, and the top left image, excuse me, I'm getting my directions mixed up. Top left image is where you have the 3D view, top right image is where you have the 2D view, just to show you the different levels of detail that you can have. In the bottom left image, we have another view of the 3D view of what it kind of looks like. And then in the bottom center there's kind of the properties that are necessary to model the BGA solder joints, but also involved in any sort of analysis that we're going to run after. So applying underfill. So answering that key question that we had very earlier, or the topic of this webinar is how to handle underfill in Sherlock. Well, here it is. It's a very simple, at least a 3-click process to do. Pretty much you go into our potting functionality within the tool. You select edit potting regions, you add a potting region, and from there you can select various shape types. So on the screen right now, I've shown you that the shape type can be the entire PCB if you're potting the entire PCB, or in this 3D view, you can see that it can partially cover a couple components. It could completely contain a few components as seen in this 3D image, or it can underfill a BGA, which is what we're doing today. So just to reiterate, it's a very simple process, a couple clicks to do that, and by taking advantage of just very simple process, and then also the materials library within Sherlock, you're able to very quickly underfill your BGA and run an analysis. So for today's example, I will be running a thermomechanical analysis. So basically, I have cycled my BGA, which I'm shown here, from -40 to 85 degrees, and seen at both those high and low temperatures what will happen, what the strains are going to look like, and will there be any issues with the underfill that I have selected. So moving forward, let's take a look at those results. So first, in this thermomechanical analysis for running from -40 to 85 degrees, we see without underfill in this particular example, nothing eventful is happening. There isn't much strain. The strains are pretty low. I'd say things are looking pretty well. We're satisfying our reliability requirements. With the underfill now, let's put this into context. There's a lot of information on this page. When we started the presentation, I mentioned that underfill has been used for quite some time. The motivation was to sort of alleviate the stresses that were being applied on the solder joints during thermal cycling. Here, we're seeing that with the application of underfill, we have significant strains that are happening at the colder end, and then not so much at the higher end, but what I want to highlight is the strains that are happening at the lower end, because these are going to be a source of stresses and strains that are going to cause failure. So in this particular situation, where clearly a bad underfill was used, we're seeing that maybe choosing underfill, with the motivation that it will help to alleviate failures. It's a great motivation, but you really need to understand your mechanical properties of the underfill material of choice. So for example, within this underfill that I've chosen, there is a specific glass transition temperature that wasn't paid attention to. So when you're cycling through this glass transition temperature, this is causing the issues that we're seeing here. Another note is that if you were interested in, for example, using an underfill or using a couple of underfills and testing those within a simulation environment, you would not per se produce this product and then figure out at the very end that this would be a problem. So after using a lot of testing, typically if you use a lot of testing, then you would see that this underfill might have been a problem, but this specific situation highlighted that this underfill might not be the best for the application. So then moving forward, you would use this information to better choose the next underfill that you would use for the specific application. So that's kind of what I wanted to highlight in this example, the fact that using underfill, it's kind of a complicated process in that choosing underfill, it's not going to be, exactly what you intended to do, and using simulation can help you to figure out which one might be the best choice. But also using that within Sherlock means it's a very easy process. So instead of, say, going into, your other FEA tools, I know by experience that it takes quite some time to fully develop a model and then apply Underfill, and it takes a lot of time. But with Sherlock, you can do these really quick what-if scenarios, and that helps you to have some really good results. So now that we have these strain values, there is a bit that I'd like to announce to our audience today. So Sherlock 6.1 is actually releasing very soon, and thermomechanical predictions for VGAs will be available. So while your other FEA tools are going to be able to give you your strain results and your strain map for under thermomechanical analysis, none of them is able to actually give you a life curve. And that's kind of been the core of Sherlock up until this point, being able to produce predictions for your products under these different environmental conditions. So up until this point, Sherlock has been in league with the other FEA tools to give you strain results for your different solder joints. In the next release, you will be able to have the power of prediction as well. You'll be able to run a thermomechanical analysis, and it will answer your questions of when will a BGA fail, for example, or when will a BGA that's underfilled fail. So you'll have the access to this very powerful and quantitative information. So just to summarize this very quick topic that I mentioned very earlier on in the presentation, that it's easy to use Underfill within Sherlock. So how to handle Underfill in Sherlock, we all should take away from this. It's a very easy workflow that gives you a lot of really powerful results. And just to show that within this presentation as well, we're seeing that system level effects are becoming more apparent with the move to higher density, higher power dissipation electronics, but also just because of the different needs that we have and the continuously evolving materials that we need to consider. Also, using a combination of reliability physics and FEA becomes important. So reliability physics is able to use, for example, the strains from my thermomechanical results and give me really good predictions for the life curve of my product. And it just so happens that Sherlock is the only software tool that really is able to give you this complete picture of your product. So with that in mind, I would like to thank everyone for listening to my webinar today, and I hope that you have a complete picture of and a complete answer of how to handle Underfill and Sherlock. If anyone has any questions, I'd be happy to answer.
Thank you, Natalie. Yes, we have lots of great questions.
All right.
So let's start with one here. What's the percentage of certainty or accuracy of the Sherlock simulation?
Sherlock simulation, so if you're thinking about putting sort of a confidence bound on the predictions, we aim for plus or minus 20%.
Great, that was quick. The filled underfill may contain defects like voids, gas bubbles, etc. Can Sherlock simulation reflect these the effects of the defects?
So if the underfill has voids and this level of defects, initially for a newer user, it would be a little bit difficult. I would say no, we wouldn't be able to do it. However, if I think this through a little bit more, if you have a quantitative understanding of the percentage of voids within the underfill, then yes, we could do something with that. But this is more of a yes or no question, depending on the level of detail that you want to get into.
Okay, great. Does Sherlock subtract out underfill from the space occupied by components / soldier balls, or does it allow the two to co-occupy space?
They do not co-occupy.
Okay, that's also quick, clear, quick.
Yeah. I mean, I can go into more detail or I can follow up with this person if they want to discuss a bit more.
Okay, another question. I'm not sure if you will be able to answer it. Can you show what you put in your mechanical properties for Underfill and Sherlock? I may have missed it, but what properties are you considering for Sherlock?
So I can do that. So what I'm going to do is I'm going to do this live. Which is, I know it's always a bad idea to try to do these things live, but I can show you within Sherlock how that's done. So we go to Sherlock and we go to Materials, Material Manager. And then within here, let's see if I can find anything. Oh, there's a potting here. There's a bunch of them. So if I double click on a potting or a material of choice, there's quite a bit of information that goes into the material definition. So at the very surface, there's the material properties. Under mechanical, there's going to be a lot of information here that's going to be important, especially if you have a temperature-dependent material. So we have modulus, CT, Poisson ratio, the glass transition temperature, and the shape factor. The shape factor itself, not to go into too much detail, it governs how the transition itself occurs. So here you're able to define your different temperatures, and then Sherlock will be able to compute. If you don't have this information, it will compute out what the modulus and CT are going to look like as it crosses its glass condition. We also have our high cycle fatigue. This is very important for things like vibration analysis. Fracture strength is, of course, not important for a polymer. And then user data, of course. So, for example, if you're within one of our enterprise accounts, it becomes very important to be able to trace who takes care of materials. So this is what that looks like. These are all the properties that you need to be able to do a very thorough comprehensive analysis in Sherlock. And just to say an FYI, if you're not able to populate all of these fields, we're more than happy to help you with that.
Thank you, Natalie. Next question. What is more important to match CTE of the underfill material with? Board, BGA material, or soldier ball CTE?
Oh, that's a good one. I'm going to need my research engineers for this one. What is more important? I'm going to say I'm going to follow up with you on that one, just because I don't want to say something that's incredibly wrong.
Yeah, absolutely. So we can follow up later on.
Sorry?
We can probably follow up with later on.
Yes. I have an inclination of what the answer might be, but I prefer not to embarrass myself.
Understood. Next question. You show an example of degradation in soldier strain with this quote-unquote wrong underfill. Do you have an example that Sherlock predicts an improvement in soldier strain with underfill?
Oh, yes, I do have it. So for this specific example, I wanted to just throw a bad underfill under there just to demonstrate that, the motivation for underfill was to alleviate the stresses that are on these solder joints. However, sometimes you can have such a bad mismatch that you have an increase in strain that's happening. So there are examples of when you apply underfill. There are Sherlock examples specifically that when you apply good underfill, you will see an increase in life. I hope this answers the person's question.
I hope so too. A couple more questions. We have quite a few questions, so I hope to get them through all of them. Is Sherlock able to predict cohesive failure of the underfill?
Ooh, that is what can I say about that? I can safely say that it is something that is currently in development. So currently we're not able to do it, but we are collaborating with one of our customers to be able to do that. That's, I think, what I can say right now.
Excellent. Can we expect it at 6.1 or no?
Oh, that's probably more of a next year kind of activity. It's in the how do I say, the testing phases at the moment.
Sounds good. Next question. You have explained for multi-layer FR4, for example, but do you have also ceramic or IMS material in the database?
Oh, that's a very good one too. So IMS will be in 6.2. So the ability to have IMS and that affects certain components, and the life curve of certain components will be available in 6.2, and that's releasing early next year.
Great. Next question. Do you have correlation to test data with Underfill?
Absolutely. Anything that anything that goes into Sherlock, any of the analyses, any of the models, they are thoroughly verified and validated using literature reviews, in-house testing, and customer test data as well. So yes, before anything is released within the tool, there is an extensive test procedure that we require.
Great. Can I simulate an assembly with no underfill?
Of course.
For example, a large BGA being soldered on a PCB.
Of course, yes. There are many levels of detail they can do. You can do that at the component level. You can take advantage of Sherlock's sub-assembly tool that allows you to build, as you would expect, different, you can have an assembly made of several circuit cards, or you can use the sub-assembly tool to build a BGA in great detail as well. So yes, the answer is yes to that question.
Great. Any comments on using underfill with a separate potting process and Sherlock's ability to handle this?
So what's going to drive the failure, not failure mechanism, so sorry. What's going to drive the life of the solder joints, so to speak, or the BGA, is going to be its interaction with the underfill material itself. So the process doesn't become as important when we're talking about fatigue behavior. And again, I would need to follow up with this person just to make sure that I'm understanding his question correctly. But basically, the mechanical properties that I showed earlier when I went into the tool, those are what are going to drive your fatigue behavior. So your final modulus or CT or the final application of the underfill material is what's going to be important, and that temperature dependent property is going to be important as well. So anything that happens before the application of the underfill, so the process involved before, is not going to be accounted for within Sherlock.
Can Sherlock consider flux residues or clean PCBs?
It is on our radar, but not at this point, no.
Can Sherlock simulation add confidence bound for the life probability of failure prediction?
Can you read that one more time, please?
Can Sherlock simulation add confidence bound for the life/probability of failure prediction?
So if you think about what Sherlock's doing, right? So Sherlock assumes a Weibull distribution, and typically, so that's just a statistical distribution. And if you think about confidence bounds on data, it's typically from experimental testing. So would Sherlock be able to give those kinds of bounds? I want to say the 90%, 80% no, it would not be able to give confidence bounds. However, I'm thinking through, there are parameters that we can change to maybe give a good estimate of what your range of results would look like. But again, my initial answer is going to be no, but thinking it through, I think it's something that we could probably work through with you.
Great. Next question. Does Sherlock take into account the effects of underfill expansion in the z-axis that may lift the component off of the board during thermal cycling?
Absolutely. So actually, this specific example, what you'll see that'll happen because there was a bad underfill that was applied, you'll see that at the very low ends, there's very high strains that are happening. It's going to cause a bit of a compression of the solder joints. And then at the higher temperature, you'll have a bit of, how do I say this, bouncing back, so to speak. So it'll compress the solder joints at the -40°C, and then at 85°C, you'll see it pry the solder joint off the board. There's a really good paper that shows this by Max and Sarah Burney, our research engineer, that shows exactly what I'm talking about. You'll see this sort of compressive behavior at the lower end, and then at the higher temperatures, when things sort of bounce back, the solder joints actually pried off or completely destroyed at the higher end. So I think I'd reference that paper as a recommendation to answer the question.
Great. A couple more questions and we're almost done. What is the definition of good underfill?
Oh, that relates to the question that was asked earlier, right? So what the CT of the underfill, should it match the bore, the component, the solder joint? And the definition of good underfill, the first thing is that if you are thermal cycling over a certain temperature range, you probably don't want to cycle over a TG or over the material's TG. For example, if the underfill glass transition temperature is at 20°C and you are -40 to 85 for your thermal profile, that may cause problems. And again, it's kind of hard to get good underfill to do that, to have a glass transition temperature is much higher. The second thing I would think, again, would be to have a good match between the, have a CT match between the board and the, how do I say, the component itself. So to answer the question I was asked earlier, what do you match to? I would think you match to the board. I think that's going to be my answer for both those questions. If you have underfill material that has a CT that matches to the board, and board warpage is going to be decreased as you thermal cycle through whichever profile that you have. And then that would alleviate any sort of stresses or prevent any sort of stresses on the solder joints themselves. So what's going to drive, this is going to be a long-winded answer, what's going to drive the failures of the solder joints is the kind of shear stresses that you have or tensile stresses that you have applied on the joints itself. And this is going to be because of the interactions with the underfill material and the board and the underfill material and the component. And a lot of that driving stress is going to be from the board itself. It's much bigger. So long-winded answer, short answer is to have a good underfill. Look at your glass transition temperature, look at your board properties, but really and truly run simulations and figure out, you know, what's going to work best for you before you even go into testing. Use the power of simulation to really complement your testing and to really help you to do more strategic testing, I think is my answer.
Got it. Okay, and next question. Can orthotropic material properties be able to input into Sherlock for components and potting? Orthotropic.
Yes, orthotropic properties. So it is, again, it is in development right now. So orthotropic properties can be within the underfill materials right now, I believe. For components themselves, if I understand the question correctly, that's something that's in development at the moment.
Okay, got it. Can Sherlock simulate thermal shock as well as thermal cycle?
Yes.
Excellent. And last question. Is there an estimated time frame for the release of version 6.1?
I said soon. We are aiming, let's see. We are aiming for the end of the month. If there is a surprise New Year's release, I think everyone would be happy with that as well.
Sounds good. Thank you, Natalie. Thank you for everything. Thank you, everyone, for joining us today at the webinar. As a reminder, the recording and the slides will be available in our media library and will be sent out via email to you guys tomorrow. Please visit our resources pages on DfR Solutions to learn about upcoming webinars and to read our